of what we're supposed to be learning today. First and foremost, we're going to go through the simple application of thermal expansion. I think everyone has definitely seen this experiment before, right? You know, in primary school, the teachers love to do it with a hoop and then a metal ball. In a normal scenario, the metal ball will go through the hoop very easily. And then after that, the primary teacher will take the metal ball and heat it up. Then after that, when you put on the metal hoop, you realize that it cannot go through anymore. It's resting there, right? That was probably the first time I experienced thermal expansion, at least in the described environment now, right? So we're going to learn about thermal expansion and the applications of thermal expansion. Then we're also going to learn about the thermometers, how a thermometer is actually supposed to, if you put a thermometer in hot water, right, by right, the temperature is supposed to increase, right? But in this scenario here, the temperature actually drops a little bit before it increases. I'll tell you why later on. Then we'll also learn about the calibration of a thermometer. Calibration of the thermometer is essentially printing the scales onto it. How do I know where am I supposed to print the 0 degree mark? Where am I supposed to print the 100-degree marks? And then after that, how am I going to scale it? That is essentially the calibration of a thermometer. Then this part here is super duper important. It is talking about the sensitivity, linearity, responsiveness, and range of a thermometer. Contrary to what most students believe, they always tell me that sensitivity is how fast the thermometer can read. That is absolutely not true. Sensitivity is basically how small of a range you can read in terms of the temperature. Like for example, 0.1 or 0.01, the smaller the number is, the more sensitive it is. Linearity, responsiveness, and range, I'll go more in detail about that later on. And finally, we're going to learn about the most complicated thermometer there is. You can kind of imagine this is like a thermometer on steroids. It's called a thermocouple, right? It can measure super large range temperatures, guys. So it's essentially a thermometer on steroids. So yeah, after that, it'll be all questions here. I doubt I'll be able to finish the chapter today though, so we'll probably stop somewhere here or here, depending on how fast the pace goes. Okay. So, talking about thermal expansion here, I'm pretty sure everyone is accustomed or at least have a fond experience of thermal expansion. Like what I had was basically the metal ball and then the metal hoop, right? This metal hoop has a diameter exactly as this metal ball here. In normal scenario, he'll be able to push it through, right, without any resistance. But then after that, what my teacher did was he started heating up this metal ball. When he heated this metal ball, what happened was obviously the ball started to expand a little bit, right? And when it expanded, it could not go through the hoop anymore because it was precisely the same diameter and it was kind of resting on the diameter. On the metal hoop, right? This here was the first experience of thermal expansion for me. In terms of thermal expansion, you have to understand why the thing expands. If we think about the solid particles in terms of its molecular structure, right? Solid particles, like we mentioned just now, they actually kind of vibrate in fixed positions, right? If it's vibrating in fixed positions, usually we don't feel that it's vibrating because the vibration is just so little, right? It's very, very small and at a very, very high frequency. What happens is, right, when I start supplying heat energy to this metal ball here, right, these particles, they gain energy, right? And when they gain energy by right, they should have a higher kinetic energy. But because solid particles, the bonds in between them are so strongly held together that they are unable to break apart. And because of that, even though they gain energy and they gain more kinetic energy, right, they will not be able to break apart, but instead they will vibrate in a larger space here. And this vibration of a larger space is essentially what is happening to thermal expansion. If you want to think about it, no heat, the thing is just vibrating. With heat, it's like vibrating and taking up a larger space in all directions, and thus this is thermal expansion. Of course, heat expands, the opposite will be true as well. The cold is actually going to contract because yet again, all this is dealing with energy, right? And when you have less energy, obviously you'll have less kinetic energy. And when you have less kinetic energy, you'll vibrate in a much smaller space and thus giving the illusion that it is contracting, right? So this is the science behind thermal expansion and cold contract. If you look at the first statement here, when heated, solid, liquid, and gas gain thermal energy, the particles start to move about more. Their vibration takes up more space, So there is expansion in all directions here. This is essentially cold, this is essentially hot. You'll see that the particles did not gain sizes. It's just that they vibrate in a larger space here. So it seems like there is expansion in all directions, guys. Then the opposite is true as well. When the temperature falls, the materials will get smaller, right? From hot to cold, obviously they will vibrate in a smaller space, and thus they will contract, right? Liquid definitely expands more when heated than solid because of their weaker bonds. Today, if I heat a liquid, right, it's much easier for them to expand because the forces of attraction between each particle is much less, right? Oh, sorry. So when heated solid expand because of vibration force them apart. You can think about it. Yeah, it is vibration, but the vibration doesn't force them apart. It's just that each and every one of these molecules here, they vibrate in a larger space, So because they vibrate in a larger space, it seems like it's expanding, but in reality, they are just like vibrating and taking up more space. You understand what I'm talking about? Good Ling. Understand what I'm talking about? Did that answer your question? Did that answer your question? You're mumbling a bit, Good Ling. Just try to give me.
I understand.
Yes, that's the best, Kun Ling. The mumble. Anyways, looking at this fifth statement here, gases expand more when heated than liquid, obviously because the gases have the weakest forces of attraction, right? And because of that, very little energy is needed to overcome the forces of attraction here. So they won't only expand, they'll actually move about in random directions with random speeds as well. Okay, so in conclusion, first things first, you have to understand is the gases will expand the most, solids will expand the least because of the forces of attraction, right? In terms of applications of hot expands and cold contracts, the most common one is basically these high tension cables. If you look outside of your house through the window, you'll probably notice some high tension cables, and you'll notice that the high tension cables will always be in a slanted manner here, never in a straight manner here. Why do they build it in a slanted manner here? If you think about it, right, in terms of engineering and cost efficiency wise, by right, a straight wire, a straight high tension cable will be shorter, right? It will be like, this will be like maybe like 3 meters, and this will be maybe like 3.3 meters here, right? By right, in terms of a cost point of view, of course, I should minimize the cost and make it as short as possible, right? But in reality, we know for a fact that this will never be the case. Why? Because if today I were to construct it in a straight line like this, right, I'm basically not allowing any room for contraction, Like for example, on a rainy day, what's going to happen is temperatures are going to drop, right? Especially at night when it rains. And when nighttime rains, what's going to happen is it will contract more. When the cables start contracting, what's going to happen is they will kind of build a force, a tension among the strings, because this part is trying to contract, this part is trying to contract, and eventually they'll contract and pull themselves apart and eventually breaking their own strings. Now, this will be much more applicable in the colder countries, like for example, Canada, America, or any country that has winter in it. In reality, what's going to happen is we are always going to construct our cables in a slanted manner here, because the slanted manner, if it's hot, right, it doesn't matter, right? It's just going to expand more. If it expands more, then just let it slant downwards. That's not an issue. But when it is cold, maybe it will contract to a maximum straight line only. It will not pull itself apart, and thus reducing some hazards, right? So this is the most applicable understanding of thermal expansion. Usually the high tension cables, you just look at all the electrical poles, for sure is slanting, because they have to take into consideration cold days, right? The second applicable application of this hot expand and cold contract is basically the railways. If you've ever taken an MRT or LRT or any train before, right, you look down onto the railing, you'll notice that there are definitely gaps in between the rails. Why this is so is because when the train passes by, obviously it's going to produce friction, right? When it produces friction, obviously it will generate heat, right? When it generates heat, obviously this thing here is going to start expanding, right? Sometimes the engineers they do not take into consideration the full expansion of the temperature. Maybe sometimes it's like the temperature suddenly gets super hot due to global warming, right? And then it gets super hot and it exceeded the calculation of the engineers, right? When the heat expansion exceeds the calculation of the engineers, what's going to happen is this is going to expand this way, this is going to expand this way, and eventually one of them is going to buckle upwards, you know. And when it buckle upwards, this is when shit goes down. Basically, when the train is coming here, you see this buckling here is kind of lifting you upwards, right? So when the train goes upwards here, that is always not a good sign. All right. I think the last train incident that happened like this was in 2016 or 2017. I can't remember if it's Japan or Hong Kong. Basically, the train, it was probably like summer day. The train was moving at quite a fast speed, and then the expansion exceeded the calculation of the engineers. So when the train came, obviously it flew up and then it toppled down, and I think it killed like 7 and injured 100 over people, if I'm not mistaken, if my memory serves me well. But hey, do your own Googling, right? But this is actually one of the super common dangers with railways. You can't make it too big because if not, the train wheels are going to drop down. You can't make it too small so that the railways, when they expand, you know, it just buckles onto each other. Then that's when very bad shit is going to happen, right? So, and the final one is basically high-speed planes. If you ever think back about the pre-pandemic days where you can still travel overseas, if you sat on the window seat before, you always notice that the wings, they kind of have like, they segment it, right? They segment it like there'll be space in between each of the wings here. This is because as the plane flies very, very fast, it collides against a lot of air molecules, right? A lot of air molecule collision is obviously going to produce friction. And when it produces friction, obviously, it's going to generate heat. So it's just the same thing all over again. Right? So these are the simple applications of thermal expansion and why we should take heat expansion into consideration. Anyone's got any questions that they want to ask or want to add on anything? Okay. Yeah, if not, then just copy this down real quick. Oh, it's here. Then we'll move on to the next part. Okay, if you move on to the next part here, this is basically a story to tell. Right? So let's imagine today I have like a hot cup of water here, right? Let's say the water is at 100 degrees Celsius. 100 degrees Celsius. By right, if I put a thermometer in here, right? If let's say initially the thermometer reading was at room temperature 24 degrees Celsius, as soon as I put the thermometer in, by right, the liquid levels are supposed to rise all the way until it reaches 100 degrees Celsius, right? This is what everyone thinks is going to happen. But in reality, it did not happen that way. Instead, the temperature, as soon as I place it into the hot water, right, the liquid levels actually drop a little bit. It'll drop a little bit first, then only it will go all the way upwards. Why do you think the liquid level drops here? Anyone wants to give me a wow guess before I call out some names? Don't worry if you don't get the right answer. I just want to see how your imagination is going to work for you. Anyone wants to take a wow guess? If no one wants to take a wow guess, then Manasvin, since you have not been here for a while, why do you think the temperature drops in your opinion?
Sorry. Why do I think the temperature drops?
Yeah, the liquid level drops first before it rises to 100 degrees Celsius. Why?
I don't know. I was waiting so that someone can answer and then I can understand.
Okay. Shamin, how about you? Want to take a wow guess on why the liquid level drops before it rises? Shamin.
Is it because it expands?
Very good. Which part expands?
Like the liquid. No, the mercury thing inside the thermometer.
Not exactly.
Oh, wait, is it the glass?
Yes, correct. Excellent guess, Charmaine. That is the exact answer. Yeah, good try as well, Kunling, but it's not the evaporation. Yeah, good, very good, Charmaine. That is a very logical and educated guess. As soon as I put, can you guys imagine this? As soon as I put the thermometer into the hot water, the heat levels will not penetrate through to the liquid straight away, right? Instead, it will actually kind of heat up this glass bulb here first, Mark. When you see, see it worked out. I got but as soon as you place the thermometer into the hot water, right, what's going to happen is the glass is the first in contact with the hot water, and thus it causes the glass to expand a little bit. When the glass expands a little bit because it is a solid, right, then naturally the liquid level is going to drop a little bit here. But usually we won't take the readings here because we'll wait for the liquid level to stabilize, meaning to say we'll wait for the heat to penetrate through the glass to touch this mercury or alcohol liquid here, and then because the liquid expands more than solid, right, naturally you'll see that the expansion is going to be much more than the drop itself. You guys get what I mean or not in this concept, in this part here? Anyone confused or want me to repeat this?
Can you repeat it?
Sorry, what do you say?
Can you repeat it?
Okay, so the concept here is that you understand the first thing that comes in contact of the hot liquid is going to be the glass bulb. If the glass bulb comes in contact with the hot water first, it will cause the glass bulb to expand a little bit. This little expansion of the glass bulb will cause the liquid level to drop a little bit here, right? And when it drops a little bit here, eventually the heat is going to penetrate through the glass bulb and touch and kind of heat up the liquid levels here already, right? When it heats up this liquid here, liquid will expand more than glass. That's why you can see that the rise is much more than the fall. You understand what I'm talking about? Cooling. You understand what I'm talking about?
A bit slow right now. I'll understand later. I'll just read up on it.
Yeah, maybe I'll show you the structured expression, the structured statements, then it'll be much easier. If you look at this statement here, is essentially what I've just mentioned, just that in a more structured manner. Initially, the indicator drops because the round conical flask expands when heated. Initially, the heat is going to reach the glass bulb first, causing it to expand. Later, the heat reaches the red ink, causing it to expand. The heat will penetrate through the glass and start expanding the liquid here. The indicator continues to rise as the expansion of liquid is definitely higher than solids. You get what I mean? Does this make more sense to you?
Oh yeah.
Yeah, correct. Nice. Yeah, copy your reading down first. Anyone still not clear with this? I can repeat. This one here comes out in your IGCSE one. I've seen like a few years asking about this question, or at least a concept related to here. If they ask about why it drops before it rises, there will be usually two concepts. Because number one, the heat expands the glass first, then it drops. Then why the liquid expands more is because liquid in general is supposed to expand more than the solid. Meaning to say the solid expanded a little bit, the liquid expanded much more. That's why it goes up. Does this mean that the temperature reading would be inaccurate? Yes, it will be inaccurate. That's why in most of your experiments, right, they'll always say for you to wait for the thermometer's reading to stabilize before you take reading, right? You cannot like straight away put it in and then it's like, oh, it's 27, oh, it's 30, it's 35 or whatever. You need to wait for the liquid level to stabilize first, meaning to say it's going to take some time, right? Then after that, only you take your reading. You get what I mean, right? Does that answer your question? In fact, since we're talking about this right now, later on when you guys do paper 6 questions, anything related to thermometer, right? They'll ask you like, what are the precautions you need to take before you take reading from a thermometer? You're supposed to say the standard 2 answers are is number 1, the thermometer must not rest on the flask, right? Meaning to say the thermometer must be in the water, not touching on the flask, because the heat could straight away heat up this thermometer here. And number 2 is usually you must wait for the reading to stabilize before taking the readings on the thermometer. Quite a standard question, quite a standard answer. You'll see it later on when we're doing some paper 6 questions. Okay. Yeah, then after that, the next part here is essentially how we calibrate and use a thermometer. Now, if you ever notice a thermometer, right, you'll notice that actually thermometers only come in two specific colors. Number 1 is either going to be silver in color, which means to say it is mercury liquid inside, or number 2, it's going to be red in color, which means to say it is alcohol inside the thermometer. Now, in your IGCSEs, these are the only 2 liquids you can use in a thermometer because these liquids are known to expand linearly with temperature change. For example, if today, right, I have a linear expanding liquid, let's say this is my thermometer here, right? If I have a linear expanding liquid, what's going to happen is the distance between each reading is going to be consistent one, like for example, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the degrees and everything. The distance between each reading is going to be the same is because we assume that these liquids have linear expansion to temperature. So like 1 cm is going to expand by 1 degree Celsius is going to expand by 1 cm, 2 degrees Celsius is going to expand by 2 cm, 3 degrees Celsius is going to be at 3 cm, and so on. And because of this assumption, we can use linear scales here, meaning to say they are all equally spaced on. Okay. Today, if you try to be funny, right, and you make a thermometer with apple juice, orange juice, or even your own saliva, right, you'll notice that the scale is not going to be correct for sure. Why? Because other liquids except for alcohol and mercury are non-linear expanding liquids. Meaning to say maybe like at 0 degrees you'll be here, 1 degrees you'll be here, 2 degrees you'll be here, 3 degrees you'll be here, and 4 degrees you'll be here, and so on and so on. The expansion is non-linear, guys. That's why we cannot use any other liquids. In fact, in your IGCSEs, in your paper 2, they'll probably ask you this. They'll ask you like what liquids can be used in a thermometer, which the standard answer is always going to be alcohol and mercury. And if they ask you this in your paper 4, they'll ask you, why can we only use alcohol and mercury? And the simple answer is because they are assumed to be linearly expanding liquids. Linearly expanding liquids. Very important. Make sure you know this. Just, yeah, we'll do more questions on this later on. Okay. So if you look at this statement here, a thermometer has glass tubes sealed at both ends and is partially filled with liquids such as mercury or alcohol. Mercury is silver, alcohol is red. By the way, alcohol by nature is supposed to be colorless. The reason why it's red is because red is easier to read, right? So people, they dye the alcohol red, so it's easier to read. All right. As the temperature around the thermometer bulb heats up, the liquid rises in the glass tube. The glass tube is mounted on a backboard that is marked with units called degrees. So we're going to mark degree, and here so on. Okay. Now, how do we calibrate a thermometer before we can mark all these degrees here? Usually, in terms of measurement, everything must be first calibrated. To calibrate is to understand where I'm supposed to put the readings on. So let's imagine today I have a thermometer, right, that just came out fresh from the factory. I won't be able to say that here is 0 and here is 100, right, because this is like a wow guess, right, at this point. So obviously you can't do that. You have to say instead that it is actually, you actually need to find out where the 0 and 100 degrees is. This is when you use 2 specific fixed points. In your IGCSEs, whenever you see this word fixed points, I want you to understand that fixed points means to say that it is a temperature where I know for sure something is going to happen. The two known fixed points are obviously going to be 100 degrees Celsius, which is the boiling point of pure water, right? And 0 degrees Celsius, which is obviously the melting point of pure ice, of ice. Okay. Now, a lot of students, they always get this wrong, especially in IGCSEs, guys. You know that ice melting, as you know, if you ever played with ice before, you see like the ice is still in the cube shape and then there's water melting right beside the cube. That is for sure 0 degrees Celsius, you know. A lot of people think that, oh, the temperature is increasing, that's why the melt is melting. That's why the ice is melting. That's not true, you know. As long as you still see the ice and it's melting with water droplets beside, that is for sure 100% 0 degrees. Why? Because at 1 degree Celsius, the ice won't even melt. You won't be able to see the water droplet. At 1 degree Celsius, the ice has fully melted into water already. As soon as you see ice melting, that is for sure going to be 0 degrees Celsius. So if I have a thermometer here, in order to calibrate to find out where the 0 degrees Celsius is, obviously I'm going to start putting it in melting ice, right? Imagine these are all melting ice. It's just poorly illustrated melting ice, you know. And so as soon as I place this thermometer in melting ice, right, this liquid inside the thermometer is going to reach a certain point, right? Let's say it reaches this point here. Then I know, oh, okay, at this point here, I know it's going to be at 0 degrees Celsius. Then after that, I'm going to take this thermometer out and I'm going to place it in boiling water instead. Now imagine this is boiling water. And then there's a heat source at the bottom. Right, this boiling water will obviously cause the liquid inside the thermometer to expand, right? And let's just say like it expands to here. Okay, it expands to here at 100 degrees Celsius. Now I know that this is going to be 100 degrees Celsius, right? Then with this 0 and 100 degrees Celsius, I have calibrated it. The next thing I need to do is just divide the space equally, right? For example, if let's say like here to here is like, I don't know, maybe it's like 50 cm. It's 50 cm long. If 50 cm represents a difference of 100 degrees Celsius, then obviously every 1 cm is representing 2 degrees Celsius, right? From here, if I know that 1 cm represents 2 degrees Celsius, every 1 cm, I'm going to write a marking. Okay, this is 2 degrees, 4 degrees, 6 degrees, 8 degrees, 10, blah, 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 all the way until it finishes, right? From here, I would have successfully calibrated and marked the scales on a thermometer. But you can't mark the scales before calibration because it's not, you can't get the scales from a wild guess, right? So this is why calibration is very, very important, guys. Anyone don't understand this part here? Anyone wants me to repeat this part? It's quite important. Sometimes they will even ask you to do the calibration in your IGCSE, but I've seen that once only in all the past papers. So it's quite rare, but in case they do, at least you know. Okay, just think about it very logically. I think it's quite doable if you just try to solve it with pure logical sense, right? So if you look at this calibration process here, first 2 fixed points must be identified. Number 1 is definitely going to be 0 degrees Celsius, which is the freezing or melting of pure water. And 100 degrees Celsius, which is obviously the boiling of pure water. Having the fixed 0 and 100 degrees Celsius, the rest of the scale is made by dividing the lengths into 100 equal division. Just now I say 1 cm represents 2 degrees Celsius, right? If you want 1 degree Celsius, then obviously it's going to be every 0.5 cm, right? Then from here, if you logic it out properly, you will be able to scale the whole diagram, right? But always remember, all thermometers must go through a calibration process first. Okay, everyone? Anyone wants me to repeat this? Anyone got anything or anything in their mind that we would like to talk about? Excellent, 100% absorption rate. Yeah, 5 minutes left. I think you guys have copied down everything already, right? Let me know if you didn't. Let me just give you a quick introduction of this part here, right? In terms of sensitivity, linearity, and responsiveness, each and every one of these are supposed to represent different things. If I were to put it in layman terms, sensitivity is the ability to measure small changes in the temperature. For example, if I have good sensitivity, it will be something that can measure 0, 0.1, 0.2, 0.3, 0.4, all the way until it reaches 100 degrees Celsius. If I have shit sensitivity, my scale will be like 0, 10, 20, 30, 40, 50, and all the way until 100 here. So good sensitivity means to say it can measure super small changes. Shit sensitivity means to say it can measure no small changes, right? Like if you want to measure 7 degrees, you're going to like divide this and then like somewhere in between 70% upwards here. It's quite hard to do that, right? So this is good sensitivity, this is shit sensitivity. Linearity is like what I mentioned just now. They should have equal spacing between each and every one of these readings here. Responsiveness is usually how fast something can react. In terms of responsiveness, the thickness of the glass bulb usually plays a role. Of course, if you have a thinner glass bulb, it means to say the heat needs to penetrate through much less glass and thus be able to respond very quickly. And if you have a thicker glass bulb thermometer, it means to say the heat has to penetrate through a whole lot of layer of glass and thus will usually respond much less. Range is basically the maximum to the minimum temperature, right? For example, good range will be like anywhere that can measure -10 to 120 degrees Celsius. Shit range will be like anywhere that can measure from 10 to 40 degrees Celsius. Usually, the larger the range, the better it is, right? So in terms of linearity, it usually is equal spacing between each reading. In terms of responsiveness, is basically how fast it can react to temperature change, and range is just like the maximum to the minimum temperature, right? Yeah, this is what you're supposed to know here. Yeah, I think I'm gonna stop right here today because it's all kind of related. You can read through this, guys. I do recommend you reading through this because usually students, they have quite a bit trouble explaining sensitivity, linearity, and range, and all these kind of things. Please read through it before the next class. At least you have a rough idea of what's going on in your head. And I've actually taken the time to tabulate all the changes and improvement of how to increase or decrease the sensitivity. Please read through this. Then this thermocouple is a whole new thing of its own. I don't think any one of you guys have ever seen this before. And truth be told, I don't think I've ever played with a thermocouple before, but I know the working principle of it. It's just that I never had the time to do this thing here. Right. Yeah. So yeah, having said that, yeah, I think I'm going to stop class here today. If you have any questions, you can still use the time to clarify any doubts you may have. If not, this week there will be no homework, guys. We'll continue this chapter next week. Okay.